Okay, so now our A rules library is loaded. So let's start applying a priori algorithm as we talked about in the class. So let's go back to our script and the command to apply a priori algorithm is of course a priori, and then you have to give the transactions which are there in your data set. Now, before we apply a priori algorithm, we have to create those transactions in a manner in which a priori algorithm or A rules package could understand. And that is a specific kind of transaction. So in order to make that transaction, what we have to do is we have to create it out of our database. And the syntax is right over here. So here what we're doing is first we're splitting our data by TID. And that's what the split function does over here. So there's a function called split over here. And it will look at the data in GR. And then it will split the data based on TID, and it will group for a given TID. It will group those items which are in a given TID. So, for example, if we have, and let's assume there is another transaction called 22222, and this is apple, and this is orange, and this is pears. Okay, so we got three transactions over here. So what this statement split will do is it will create this to be one transaction, and it will create this to be another transaction. So when you look at this transaction, once it's created in a manner in which A rules understands it, for two, you're gonna see curly braces and you're gonna see apple, orange, and pear sitting in that one group. And then for one, curly braces, you're gonna see citrus fruit, semi-finished bread, margarine, ready soup sitting in one place. So this way, A rule understand, okay, this is one transaction, this is another transaction, these are all items sitting in that particular transaction. However, behind the scene, transaction data type is something that we talked about in the class. It's called sparse matrix. So, so those who do not remember or recall, sparse matrix looks something like this. So this is transaction one. And this transaction one has item 3 and item 11, and all other items were not bought, so they're all empty. And these items could be, like in our case, it could be 169 items. Similarly, transaction 2 has item 5 being bought into it and item 6 being bought into it. Everything else is empty. So this is sparse matrix, and this is how the transaction data type stores that information. That is how it is being used by association rules. So only those instances where this combination of row and column, which is this combination of item and transaction ID is populated, only those are stored in the data and others are thrown away. So there is no storage for this. The only thing stored is this and this, this and this. So the data is actually stored as a sparse matrix. However, when you look at the data in grocery, as we'll see in the next couple of steps, you'll find that it looks like one transaction ID and then curly braces and then a bunch of items in it. But this is a step where we split the data into, for a given TID, whatever items are there, they'll be grouped into one chunk. And then the output of the split will be converted into transaction because of this particular function called as. And we saw this in our previous lab 1, where I think we converted a matrix to data frame or data frame to matrix, which could be done again with as function. So once we do that, groceries has been created and it is a transaction data type of A rule. So if we do say class on groceries, you'll find that it's not saying data frame or list or anything like that. It's saying it's a transaction data type, and it is of a package called A rules. So so that is how you create transactions for A rule, so that A rule could understand, okay, this is a transaction. Now let's go to the next step. So once we have created the transaction, let's summarize. Let's see what's there in the transaction. And the syntax is very similar to what we have done in lab 1, summary, and then the transaction variable name. So once we do that, now we have all the details about this variable called groceries, which is nothing but a transaction of all the transactions which are there in our data set. So once we do the summary, we find out, okay, transaction as item matrix in a sparse format. So the sparse format is very similar to, in fact, it's exactly this format where you have these item 1, 2, 3, 4, in this case, 169 items, and then you have all these transaction, 9,835 transaction this way, and whichever item is bought that is populated, others are thrown away, and that is called sparse matrix. So now we get vital information about our transaction data set. 9835, 9,835 transactions are there, rows, and then 169 columns are there. So 169 columns. So there are 169 columns this way, and there are 9,835 rows. So that's the information from these two things. Also, it gives us some information about the density of the data. So density is 0.026. It is actually how much this data over here is populated. So is it like this, or is it like something like this? In this case, the density would be higher. So if everything is populated, let's say for example, the density would be 100% because everything is populated. We do not want it to be that way because then a priori algorithm would not be appropriate. But a density gives you some idea about how sparsely populated, low or high, the transaction matrix is. So that's an idea like how many products are being sold in amongst the transactions. Okay, so and especially like say for example, if you look at the data that you're getting from say Walmart, as you know we get at University of Chicago, if you look at the data, it is hugely sparse because here we just got 169 items, but in real life you're gonna have like 100,000 items. So this is a really high density. In reality, gonna have you will see very low density. Okay, now the other piece of information that summary gives us is the most frequent item. So right here I can find out that whole milk is the most frequent item. It is being sold in 2,513 transactions, followed by other vegetables, which is sold in 1,003 transactions right over here, and then rolling buns, 1,809, 1,715 is soda, yogurt, and others. Now, thereafter, we have more information about how many buckets are there which have just like one item in them. How many transactions were there where only one thing was bought? So there are 2,159 transactions where only one thing was bought. There's 1,643 transactions where two things were bought. There are 1,299 transactions where only three things were bought. And this number keeps going down, 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 and down. And there is only one transaction where all, not all, but 32 items were bought. So literally there is no transaction where all the 169 items were bought. And here is a basic statistics about the spread of the size of the basket. So it goes one on the minimum side, and the maximum is 32. And thereafter, we have some more information, extended item information. We do not have to worry about that. But these three pieces of information is really useful. Very quickly we find out which are the most frequent items. Very quickly we find out, okay, uh, how many distinct items are there, how many transactions we are talking about, and how the bucket looks like. So right now we know the bucket size is between 1 to 32, and there are a lot of buckets. In fact, 1/4 of the buckets have only one item in them. So we get that vital information. Okay, so let's move on to our next step, and let's look at the records which are there inside the grocery um, uh, variable that we have created, which is nothing but transaction. So, and the way to do that is through a function called inspect. So through inspect, we are inspecting groceries transaction variable. And this gives us the first 5 elements, and that is what this 1:5 means. Give me 1 to 5 records. So the first one is transaction 1. It has 1, 2, 3, 4 items in there. Transaction 2, it has 1, 2, 3. And then transaction 3 has 1, 2, 3, 4, 5. No, actually 3 has only 1. And then 4 has 1, 2, 3, 4. And then 5 has 1, 2, 3, and 4. Um, So this is a way by which we can look into these transactions using a function called inspect. But the whole point is that this transaction variable called grocery, although it looks like you got one transaction ID and then you got curly braces and all the items are sitting in there, it's actually a sparse matrix. It's hard to visualize it in this way. We'll see it when we visualize it through image command. So we'll do it in next couple of steps. Okay, let's go back to our script. Now, what we can do is we can also examine the frequency of the items, which we have done to some extent through our SQL statement. And that's the reason I think, SQL is very powerful. Instead of reading anything from R, you can just, if you're in database, you can do all these things just by plain SQL. So let's execute this command called item frequency. Once again, be cognizant of the fact that it's case sensitive. Case sensitive. So this F is capital, it's not lowercase. So if you make it lowercase, it's not going to work. And then you say, okay, give me the frequency of first three, uh, so RC first three columns in all the rows. So it gives us the first three items, which is abrasives, cleaner, artificial sweetener, and baby cosmetics. So when I say 1 to 3, that 1:3, that means 1 to 3. So if I say 1:10, that means 1 to 10. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this gives me first three items and their relative frequency. So what that means is if I look in Excel, it's talking about these three items over here. So in this case, item one is abrasive cleaner, the second one is artificial sweetener, and the third one is baby cosmetics. So so that is what is meant by this syntax. Give me all the rows, across all the rows, what is the frequency of item 1, 2, and 3. If I do, so let's do 10, and now I get 10. So artificial sweetener, baby cosmetic, baby food, bag baking powder, bathroom cleaner, beef, berries, beverage. So now I got 10. So that implies 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So give me the frequency of these 10 items across all the rows. Okay, so far so good. Now let's go to the next command. Let's plot the frequency of the items. And I'm interested in plotting those items that have support equal to 1. So how to do that? So the command is item frequency. Again, F is capital and P is capital over here. So be cognizant of that. And then I'm going to put I'm going to supply the transaction variable name, which is groceries, and then comma, and then support equal to 0.1. That implies 10%. So I'm only interested in those items that have support of 10%. So once I do that, I get all the items which have support of at least 10%. And so this one is somewhere around like 11%. Here you got other vegetables, which is high. Whole milk, of course, is 25%, and yogurt is somewhere around like 11, 12%. And this one is more like 17%. This is more like 18%. So these are all those items that have support of at least 10%. Okay, so that was the way by which I can plot items which meet at least 10% support, minimum support. And then I can do the same thing with in terms of rating, give me the top 20 most frequent items. So once I do that, I find out that whole milk is the most frequent item. And again, it's frequency about like 25%. And it's there in 25% of the buckets. And then other vegetables are there, rolling buns is there, soda is there, yogurt is there, and so on and so forth. But uh, the same command item frequency plot, it plots the item across based on the frequency. And you can do it either by supplying minimum support, or you can do it by saying, okay, give me the top 10 or top 20. So if I do top 10, uh, not 0, top 10, and this give me the top 10. So this is another very useful function that I very often use. Now, since I told you that groceries is a sparse matrix, you can actually visualize it that way, and that is what we do with a command called image. And image, um, give you a graphical visualization of how the data is laid down in a grocery um, transaction variable. So here uh, we get this kind of feeling that it's very much like the data the way we had over here, uh, right over here. We get this kind of feeling. However, the data is not like this. Data is actually like this in a sparse matrix format. So when we visualize this data through image command, this is the first transaction. This item was bought, and this item was bought, and this item was bought, and this item was bought. So there are four items in the first transaction. The second transaction, this item was bought, and this item was bought, and this item was bought. So there are three items in there. And then the third row, no item was bought except this one, and we know that's a whole milk. So it seems like so that is whole milk, and fifth transaction also had whole milk. So let's see if fifth transaction had whole milk. Yes. So fifth transaction also had whole milk. The point is, this is how the data is sitting in that groceries variable. It's in a sparse matrix format, and you can visualize this way. And right now we are just looking at say 1 to 5, but I can increase the number. So let's see, let's look at say 100 rows. And once we do that, we see a random pattern. The one thing that I talked about in the class is that why this is useful. Can you draw some inference out of this, some knowledge out of this picture? Uh, One of the very quick thing that you can realize out of this picture is that is there anything that is being bought all the time? So if something is bought all the time, what will happen is that that particular item will always be populated. So it will always have this black dots over there. So in that case, these black dots will form a line, a straight line. So if you see a straight line, good number of times that could be because of one thing, that when you retrieve the data, it had some identifier related to location or a store or something coming from the data warehouse team that they did not remove. And that is the reason why you have a straight line over there. The second thing could be that when you were combining bunch of products into category, that category is such that it appears all the time. So say for example, the example I gave in the class was Starbucks. If you combine all the things that Starbucks sell into in terms of liquid into coffee, in that case, you will have those straight lines because everybody who's walking to Starbucks, they're coming over there for coffee. Almost everybody. So you'll have a huge straight line going across the entire data set, and that implies the way to work around that is that you'll have to break that category like coffee into smaller categories, which could be decaf, caf, or which could be light brew. Um, Heavily brewed or dark or light or medium kind of thing, and then you can combine it with the other variables like say time of the day or season, and then you can say that um, people in morning they tend to drink more of um, dark coffee versus say evening when people tend to prefer light coffee. So based on that you can do something about should you brew four you know vessels of particular kind of coffee in the morning or in the evening kind of decision. So the point is that if you see those kind of lines, it's a problem. You have to do something about it, and this is a very quick way of finding it out. What you're looking for, if all the things are fine, is a randomness. So if the data is random, which is the case here, that implies that everything is fine. That implies there's nothing wrong. But if you find some patterns, that's an issue. At the same time, many a times, not all the time, you will find that there are some horizontal lines happening very often. And that implies that there are certain items which are being bought together. And this will happen only if those two items are placed next to each other. So um, when they're bought together, that implies that they need to be coalesced. They need to be combined into one category. Otherwise, you'll get some uh, misleading correlation or misleading rules, which says that whenever people buy nuts, they also buy bolts. So, well, nuts and bolts, they go together. So there's no point in putting them in separate category. Let's put them in one category. So very quickly, based on this, you can find all this information. Let's move on to the next step. Okay, and similarly, what I can do is I can also draw random samples out of out of the data, and I can visualize that as well. So here I'm drawing a random sample of 100. So 100 is the bucket size, and the sample is the command in R that make you draw samples out of a variable called grocery, and it will take 100 items or 100 transactions out of groceries out of random. And and you can see, how the picture looks like. So again, picture going to be slightly different. So every time you run it, it's drawing a sample out of groceries transaction data set. But the reason why we want to draw a random sample is that maybe there's some issues with the order, and if you draw a sample, in that case, you are not dependent upon that order. So, for example, if I just take the first 10, say 1,000 rows, uh, those 1,000 rows could be related to only uh, first 2 hours of the day of Starbucks. So it may not be the true reflection of everything that happens in Starbucks. So that's the reason why sampling may bring a more inclusive picture than just taking an ordered uh, top 100 or bottom 100 rows. Okay, the point is that through image command, you can visualize the sparse matrix, which is groceries. Okay, so now I can apply a priori algorithm because I've already converted my data into transaction. So the command for that is a priori. That's a function that comes with a rules. It will run a priori algorithm on transactions, which is stored in groceries variable, and then I hit enter. And once I do that, nothing happens. There are 0 rules being learned. So that implies nothing happened, and the reason for that is that you have to supply thresholds that we talked about in the class. The reason why a priori algorithm works is because of those thresholds. Those thresholds define what frequent is and what not so frequent is. So if threshold is, threshold on support is 10%, that implies that anything that is fewer than 10% in our data set will be thrown away. And as we move from single items to pairs to triples and thereafter the combination of 4 items, we'll keep doing the similar kind of pruning. And that is the reason why, despite huge combinations that exist, because a distinct number of items, still a priori algorithm is able to find out those relationships, is because of those thresholds. So we haven't supplied the threshold, nothing will happen. So let's supply the thresholds. So the way to supply threshold is right over here. So a priori algorithm is exactly identical to the function that we did in the previous. And the grocery is the variable that has all the transactions in it. And then we'll supply those thresholds, and thresholds will be in list. So parameter is equal to list, and this list has the first element support, which is 0.006%. 0.006, so the percent gonna be 0.6%. You multiply by 100, become 0.6%, and the confidence will be 25%. So you multiply by 100, becomes 25%, and we are only interested in those rules which have length 2. So we're interested in only those rules where it says when people bought milk, they also bought bread. When people bought milk, they also brought bread and eggs. When people bought bread and eggs, they also brought milk. So those kind of rules, they have length of either 3 or 2 or maybe 4 or 5. We are only interested in those rules. If there's a rule which has just only one element, do not even show it. So these are the thresholds that we define, and then we hit enter. And now 463 rules are being generated, and those 463 rules are put into this variable called grocery rules. So we can do similar kind of thing that we did in the past. We can do summary on the grocery rules, and we find out, okay, In the summary, it's a set of 463 rules. There are two rules. There are 150 rules that have two elements in them. There are 297 rules that have three elements in them, and then 16 rules are there which have four elements in them. And by element, I mean item. So here it would be more like milk leads to bread kind of. Here it's milk and egg leads to bread kind of. Here milk, egg, and honey leads to bread kind of rules. So that's what this means. And then there's the basic statistics of the distribution that in the minimum we got two rules, two item rules, and the maximum we got four item rules. And we look at the median and the mean, they're around the same, 3 and 2.7. And then we got um, some statistics on the support and the confidence and lift across 493 rules. So for support, we see okay, the median is about 0.8% and the mean is about 1.1%. The maximum is about 7.4%, and the minimum is about 6.6%. So you have to multiply it by 100. So there will be 0.6%. So that is the support confidence. The maximum is 66%, and the minimum is of course 25% because that was our threshold. And the first quartile is 29%, and the third quartile is 44%, and the median and mean is very much close, 35, 37%. If you look at lift, it's the maximum is 3.95%, so that implies there's some really interesting rules out there, and the minimum is about you know um, 9. So 99, that's almost 1. So that's the spread of the lift, that's the spread of the confidence, and that's the spread of the support. Basic statistics, again, everything that we talked about in the lab one in terms of how to read these statistics, you can apply that. Okay, so so far so good. Let's go to the next step. So now we have the rules. Now what to do with those rules? We have already done the summary. Let's inspect these rules. Let's see what these rules are all about. Let's look at the top three rules. Let me select this. And inspect is a way by which we inspect um, these variables being generated by a rules package. So inspect grocery rule, give me 1 to 3. So this colon means 1 to 3. If I make it 1 colon 10, it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 rules. So here is the left hand side, this is the right hand side. So left hand side is potted plant. Those who bought potted plant, they ended up buying whole milk. The spotted plant and whole milk happened 0.6% of the time, 0.69 or almost 0.7% of all the transactions that we had. The confidence of this rule is about 40%, and the lift is 1.56. That implies once people bought potted plant, the probability of them buying whole milk uh, jumped by 1.56 times. So that's what this rule means. So these are the top three rules. Okay, now not only we can see the top three rules, we can also sort them by certain features. So the most interesting feature is of course a lift. So let's sort them by lift, and let me go through this particular command. So what we're doing is we're using a command called sort, and we'll sort grocery rule. And the question is how we're going to sort. So um, by is equal to lift. So we'll sort the data, which is grocery rules, by lift, and we are only interested in 1 to 5 um, rows. So we are only interested in 1, 2, 3, 4, 5 rules, and the inspect is outside. So that's what this whole syntax means. And with that, we get top 5 rules which have the highest lift. So the first one is those who bought a herb, they ended up buying root vegetable. So once they bought herb, the chances of buying root vegetable jumped up by almost 4 times. So that is what this particular rule means. But this is the way by which you can sort the rules as well. Okay, now one of the last things that we did in the class was in case, so here I got 493 rules, but I'm not interested in all the rules. There are only certain items that I'm interested into. How to subset my rules and just look for those items. So the way to do that is by using a function called subset, and I'll use it over here. So this is what subset does. It's saying, okay, this is subset. It's saying subset grocery rule and give me only those rules where the item in this category or this name, like berries. So give me only those rules where the item is like berries. And if it's not berries, then do not show those items to me. And once you filter those items, create a subset of that, put that subset into this particular variable called berry rules. So it's creating a subset of the grocery rules based on those rules which have berries in them in item um, in item attributes. So where the items are like berries, take them out and put them into this particular variable called berry rules. So that is how subset command works. So once I hit enter, now all the rules which are related to berries are in in berry rules. Okay, so now we can do the inspection of the berry rules, and that will give us all the information about berry rules. And now we see there are only four rules because there are only four rules related to berries, which have berries in them. And these are all the rules. Of course, the first rule looks like really interesting. Those who bought berries, they ended up buying whipped sour cream. Um, Once they bought berries, the chances of picking up whipped sour cream increased almost fourfold, 3.79 times. So, but this is the way by which you can subset the rules. Okay. Now, the last thing that we did in the class, one of the last thing was to write this grocery rule into a file so that we could play with that later on. So for that, we have this command called write. So you write grocery rule variable into a file called grocery rules.csv. This grocery rules.csv will be created in the working directory that we set in the set working directory command. And this file will be separated by comma, of course, since it's a CSV, it will be separated by comma because CSV stands for comma separated value. And the quotes will be true, there'll be quotes around, and the row name will be false. So what row name means is that when I generate the file, I do not want these say 1, 2, 3, 4, 5. I do not want that counting that R does. So if I do not put row name is equal to false, if I remove this option or this parameter, it will put that 1, 2, 3, 4, 5, and it's annoying. So that's the reason I put row name is equal to false, and then I hit enter, and now grocery rules.csv is written. So let me see what my working directory is. Okay, so my working directory is RLAB02. So let me go to RLAB02 on my desktop. So I go to my desktop and there's the RLAB02 and grocery rules is created over here. So if I click over here, here I see all the rules, the respective support, the respective confidence, everything is in there. So that's great. So that is all fine. Um, okay, so that's what we did in the lab. Now, one thing more that we can do is it's another example of what we did in lab one. Here I'm taking grocery rules. It's not necessary, but I'm converting into a data frame. So again, I'm using as. If you remember, I used it a couple of steps ago to convert a split output into a transaction. So uh, instead of grocery rules, I had the command split, split gr, and for each TID group, all the items. Here I got grocery rules, and I will convert the grocery rules into data frame. And there I was converting the output of the split into transaction data type of a rule. So once I do that, it is converted into a data frame. So now if I do class on, and this is not related to association rules, just to, you know, give you some practice on conversion of the data types or uh, something that we talked about in lab one. But if you keep doing it, it will become your second nature. Okay, so it's a data frame. Once I do class, it's a data frame. And you can also write, data frame if you want to in this way into a local text file. So what I'm doing here is I'm saying write.table, and write.table will write this table, which is a data frame. So this is the data frame that this syntax write.table, this function will write. It will write to a file called grule.txt on my D drive, and we'll separate it by by pipe, and the quote will be false and the row name will be false. And let me just remove this one so that creates in the same place in my working directory. So with that, let me enter this, and so now this grule.txt should be created um, in our lab02 folder, and this is here. So it is a .txt, not a CSV file, and instead of comma, it's separated by pipe. This is another way in which you can create a text file, or you can write a data frame to a text file, and you can play with that. So now we have all our rules, and we started with data that came in, one row, one transaction. It has a bunch of items in it which were bought in that transaction. Now we have created the rules, which are in total 463 rules. So we did a lot of, summary. We started with 10,000 rows. Now we are down to only 500 rules. Now, what to do with these rules? How to choose some interesting rules, which are important rules. And that is where, Tableau comes to our help. It's a great visualization tool. It's heavily used in data mining as a way to explore data. And that is the reason I want, you guys doing a lot of stuff with Tableau. And you must have already done tons of stuff with Tableau in other classes. So now I've already written my files in text files. So let's all my variables in text file. Let me go to desktop and go to Labo2. That's where I've stored all my stuff. Okay, and I got grule. And grocery rules and G rules, they are exactly the same. So okay, let's open grocery rules as CSV, and this will open this CSV file in Tableau. And now the file is open. I can see all the columns over here. So rule is the first column, support, confidence, lift. And now I can go to sheet 1. And now what I'll do is I'll plot the confidence against the support. And by default, it will aggregate confidence support. It will summarize. I do not want that. I just go to analyze. I click over here and I see all the points over here. And each point is a rule. It corresponds to a rule. Now, um, that is all fine. I know that I'm interested in these rules over here, but I do not know their name. So I'll drag the rule and I'll put on detail. So once I do that, once I hover my mouse on these rules, I found out that, okay, this particular dot relates to other vegetable leads to whole milk, that rule. So that way I can find out which rules are interesting. I'm interested in those rules which have high confidence and high support, and these rules qualify for that. Not only that, I'm also interested in those rules which have high lift, because they may have lower support, um, or low confidence. But once a particular item is bought, then it increases the probability of the other item being bought tremendously if they have high lift. So how to incorporate lift in this picture? And that's where the idea of color comes. So I will drop lift onto the color. And this opens up a shade of green, which doesn't tell me much. So I will change the color scheme, and I can make it something like, say, area red green divergence, and I'll make it stepped color so that I get a good idea about how big that lift is. And then I do apply, and now I know that if it's really dark green, that implies it has ultra high lift. So there's some dark greens over here. If I hover on them, then I get, okay, this is 3.6, almost 3.7 lift in there. So this could be one of the rules. Although it doesn't have really high support, it doesn't have that high of a confidence, but it has really great lift. So this is a visualization through which I can pick up some really interesting rules, and I can run it through my domain expert, or I can further dig into the data. But uh, association rule is a very good way to parse through a very large amount of data with tons of variables in there, and visualize it very quickly and figure out how these variables are related to each other. So that is what a lab 2 exercise is all about.